is a solution video to the first set of practice problems for the alkene chapter. In this video, we're just going to be doing like E versus Z designation and then ranking alkenes in order of increasing stability and melting point. In the next video, we'll have some reactions for alkenes. So for this first question, we're going to talk about E versus Z designation. And so for each double bond here, we'll go through and identify it as E or Z. So let's start with this one down here that I just highlighted in green. And so here we can see that if we were to draw in those hydrogens, we actually have the same exact substituents for that bottom carbon. And so we do not use E or Z designation for this alkene. So we don't have to do anything for that one. However, for this top one that I just highlighted, we have two different substituents on each carbon. And so we can draw in that hydrogen first. And so for this carbon on the left, we have two different groups that we could consider for our priorities. We have this hydrogen, and then we have this alkane chain going to the bottom. And so for this one, we know that that bigger carbon chain is going to win out for priorities. And so the group that we'll consider for priorities is going to be the one going down. For this carbon on the right, we're comparing this O methoxy group right here with this methyl group. And so we know that oxygen takes priority. And so for that, we will keep this top group here as our group that we'll use for priorities. And so if we look at the plane of our alkene, if we draw a line straight through, we can see that those two groups are on opposite sides. And so this will be an E isomer. Next, for the one here in the middle, we have this alkene here. We can draw in that hydrogen on that bottom right carbon. And so for priorities, we know that that hydrogen is not going to be a priority. And so this group going up is. For the carbon that's on the left, we have the option of choosing that methyl group or that carbon group going up. And so we know that that higher priority group is going to be the one going up. And so the one that we care about is going to be here. And so if we look at the plane of our alkene, we can see that those groups are on the same side. And so this will be a Z isomer. Next, we can do this final one. Here we can see that we have this plane for this alkene. And then we have hydrogens, so we're going to ignore those. And we really only care about the groups, the carbon chains that are going to the left and to the right. And so those are on opposite sides of the plane. And so this is going to be an E isomer. Next, we can do the group on the top. And so we'll draw our line through the alkene. And then we'll take a look at each of those carbons. So first we can start with this carbon on the left. And so for this, we know that this OH-CH3 is going to be higher priority because of that oxygen than the group going to the other direction. And so for that carbon, that OCH3 group is going to be the priority. For the other carbon, we have a hydrogen there. So we know that the other group is going to be the priority. And so we can see that these two blue groups here are on opposite sides. And so this is also going to be an E isomer. All right, let's move on to the next one. So here we're going to rank the following alkenes in order of increasing melting point and boiling point. And as a reminder, generally when we're comparing melting points and boiling points, the overall structure has to be roughly the same size. If you're comparing like a really, really big structure, then you're going to have different contributions to the intermolecular forces. And so at that point, it might not be enough to just compare the alkenes by themselves. But here we have roughly the same sizes, so we can use our rules that we talked about in the notes to determine which ones will have a higher boiling point or melting point. And so let's start with this one. We can see that this is the most substituted. And also we have a smaller surface area. Everything's a little bit more compact. And so that matters for those intermolecular forces that we would get. And then we can also see we have no net dipole because all those groups cancel out. If we were to draw in the individual dipoles of all of those carbon chains, we can see that they all cancel each other out because they're all just coming in from different directions. And so the ones opposite each other cancel out. However, for this middle one, we can see that we have actually a small dipole going inwards. And so we end up with an overall dipole going down that I just drew out in purple. And so we do have a net dipole here. And then we also have a less substituted alkene. Here for this last one, we don't have a net dipole because all of those, the ones coming from the edges cancel out. They're in opposite directions of each other since we have a trans alkene. And then we also have a slightly larger surface area in comparison to that first one and a less substituted alkene. And so in ranking these from lowest to highest, we know that the one with the net dipole is going to be the highest because that contributes to intermolecular forces that the compound would have. And so this would be the highest BP and melting point. The first one here is going to be the lowest, and that's primarily because we have no net dipole, and then also we're just really small and compact, so there's less surface area for intermolecular forces. And then finally, that last one is going to be intermediate, and that's primarily just method of kind of, we already know which one's the lowest and highest. All right, let's do this last question. So here we're ranking the alkenes in order of stability. And so for this, we care about the substituents that each alkene has, and then whether they're cis or trans. So let's go through and label each alkene. So this first one's going to be have 2 substituents, and it's cis. This next one has 3 substituents. This third one has 1 substituent. And then this last one has 2 substituents, and it's trans. And so we know that the 1 substituent is going to be the least stable. And that's because the more substituents we have, the more stable we are. That means that the second one is going to be the most stable. And then finally, we can do that first and that last one. And so for the first one, we have a cis double bond. And for the last one, we have trans. And so we know that trans is going to be more stable. So that one's going to be 3, and this one's going to be 2. All right, so that wraps up this video. And again, in the next video, we'll have some reactions that we'll do some practice problems with.